Hello, everyone. Good morning, good afternoon, good evening, wherever you are. I am Peter Doherty, IBS Executive Director, and I'd like to welcome you to the March Journal Club session. These sessions are complimentary, available to all IBS members, with the primary purpose of providing a platform for individuals to present worthy papers in a public setting and to widen the scope of understanding for these papers. Additionally, we want to provide a networking opportunity for IBS members through the Journal Club. Thanks as always to our chair, Jen Lee of the University of Michigan, who is with us today, for supporting this program. And Jen, if you'd like to welcome everyone, the floor is yours briefly.
Hi, everyone. Welcome. Welcome to this special session. We certainly have some worthy paper to present today. That this special edition of the Journal Club is also considered an International Biometric Conference 2024 session. So as with other IBC 2024 sessions, we were unable to hold the following sessions in Atlanta due to travel and other related issues. So but that doesn't stop us. So we're pleased to have our presenters here to present 3 of the winning JABES best papers from 2022 and 2023 volumes. So speaking today will be authors Peter Gao, who is Assistant Professor of Statistics and Data Science in Department of Mathematics and Statistics at San Jose State University. Also Joshua North, who is postdoc Cascade postdoc research fellow at Lawrence Berkeley National Laboratory. And last but not least, Dr. Bo Li, who is Stanley A. Sawyer Professor of Statistics and Data Science in Washington University in St. Louis. So they will, well, first of all, congratulations to all 3 of you on this best paper accomplishments. But before I go any further, I would like to hand things over to the executive editor of JABES, Jorge Mata, to provide a little bit of background into this award selection process. So Jorge, please.
Yeah, thank you very much, Jen. And welcome everyone to this session. Just some quick words to see how this works. The thing is that years ago, we started these JABES Awards for the best papers selected in those papers published in one particular year. We started in 2022, and then basically today we are offering the possibility of the winners to present their papers for the winners of 2022 and 2023. Let me just give you some particularities on how these were selected. The idea is on the very first thing, the editor-in-chief selects around 40% per issue of the published papers in one particular year, right? So basically we have 4 issues a year, and on average we are publishing 10, 11 papers per issue. So basically 40% of them are selected in a very first screening process. Then these selected, they go to a pool where all associate editors are invited to vote. And basically we're voting for giving 1, 3, and 5 points, depending on let's say the way we're gonna give to each one of the papers. And at the end, after 1 month, we open the poll for 1 month. After 1 month, we just collect and summarize all the results. Basically, at the end, what we have is per year 1 winning paper, and 1 honorable mention paper. So basically, we have 2 winning papers per year. So basically, today we are offering the possibility to provide the presentations to the 2 winning papers from 2022, and they were embedded in 2 winning papers for 2023, but only 1 will be presented today. So basically, my very last message is that these selected papers have gone through a screening process first, and then through a selection through all the associated boards. So it means that they are really high standard and very high quality papers. So basically, we really congratulate those winning and honorable mention papers. So I just want to say this because I think we need to be very proud of these papers selected from those published in JABES. Thank you.
Thank you, Jorge. I have just a few housekeeping comments before we get started. This session is being recorded and will be available for replay early next week. which is typical for all of our journal club sessions. Please mute your microphones throughout the session if you're not speaking. You will have the opportunity to ask questions during the Q&A period at the end. And you may also ask questions via the chat feature, and we'll address them during the Q&A portion at the end of the presentations. But we'll be actively looking for questions in the Q&A tool here in Zoom. And now we're pleased to have presenter Peter Gao offer his group's award-winning paper from 2022, which appeared in volume 27 of JABES. All participants are encouraged to engage in the discussion and ask questions, and also let us know how we can use or apply these methods to our work. Peter, I will hand the floor over to you, and thank you for being here.
Great. Yeah, thank you so much for that introduction. Thanks to the journal and IBS for organizing this session. I'll just get right into it. Today, I'll be talking about some work that I carried out while I was a graduate student at the University of Washington, with some collaborators, Hannah Director, who's now at Health New Zealand, and Cecilia Bitts and Adrian Raftery, who are both affiliated with UW. I also want to thank Noah, who supported this work and helped me to carry out this research. So today I'll be talking about a project called Probabilistic Forecast of Arctic Sea Ice Thickness. And to motivate this work, I first want to explain what I mean when I say Arctic sea ice thickness. So for most of the year, the Arctic, or much of the Arctic, is covered by ice. It's kind of like a floating pack of ice that grows over the course of the winter and then melts partially during the summer. So on the right here is a map of last year's minimal sea ice extent, so the point at which it was the smallest over the course of the year. It's provided by the National Snow and Ice Data Center, and we can see here that it was in September 11th, 2024. This yellow line on the plot represents the median ice age, or ice edge, over the course of, let's see if I can reshare. Maybe that'll help.
I see it now, Peter.
Are they changing? Okay,
Yeah.
great.
Yes, looks good now.
Thank you so much. So as I was saying, this represents the kind of minimal ice extent from last fall. And then this yellow edge represents the median ice edge over the last 40 or so years for comparison. I believe it's the minimal median minimal edge. So as temperatures have been increasing in recent years, there's been a lot of growing interest in predicting whether this ice pack will continue to be a permanent feature of the Arctic, or maybe if it'll start to melt out completely in the summer. I looked at some recent headlines, and here's a recent study from Nature Communications that predicted that we could be seeing ice-free summers in the Arctic starting by 2030 or sometime around then. This is potentially of interest for all sorts of purposes, including practical purposes such as shipping lanes, but also because the sea ice plays a major role in regulating both the Arctic and global climate. Essentially, there's a well-known feedback cycle where since sea ice is highly reflective, as it melts, the ocean starts to absorb more heat, which then, of course, leads to faster melting. So this project is really interested in trying to understand sea ice thickness, but it grew out of a series of projects led by my collaborator, Hannah Director, who is another of Adrian's students at the time. And her projects focused largely on post-processing of forecasts from physics-based models of the climate. In particular, her work really focused on post-processing forecasts of Arctic sea ice extent, which really just means the surface area of the ocean that is covered by the ice pack. So here's a graph also from NSIDC of the annual sea ice extent over the last few years. This dashed line is 2012, which is sort of the historic minimum that was observed. And we just see the last few years here as well. And so Hannah's work really focused on producing calibrated probabilistic forecasts of sea ice extent based on existing physics-based models. And our goal was really to do the same for sea ice thickness, meaning the thickness of the ice pack at each location. Now, sea ice thickness is a little bit more difficult to observe than sea ice extent. Here's a picture of some sea ice taken by Megan Ferguson, who was taking this from a plane flying over the ice pack. You might imagine that for a given location, you can take an image and basically just decide, okay, is this location covered by ice or not? If so, include it in the sea ice extent. But thickness is a little bit harder to measure, and typically relies on satellite-based estimates of what's called freeboard, which is the height of the ice floating above the water. And so for this reason, while existing physics-based models do try to produce forecasts of sea ice thickness, many of them are subject to bias and somewhat improperly calibrated. I should note now that a lot of this work is from a few years ago now, and unfortunately, I haven't had the chance to keep up to date with all of the progress in this field. But I'll talk about this idea as kind of a proposal of a post-processing method, right? So our goal for this project is to generate probabilistic forecasts of thickness in terms of intervals for individual locations thicknesses and also for overall sea ice volume. And so in order to get these calibrated forecasts, we need to generate some sort of model for the sea ice thickness that is sort of marginally calibrated at individual locations and times, and also jointly calibrated in that we can kind of aggregate forecasts to get reasonable predictions of aggregate quantities like sea ice volume. I want to note now that also the ice is not exactly smooth. It's filled with holes and small melt ponds as you travel along the surface. But for the purposes of modeling, it's often treated as kind of like a continuous block of floating ice. And so while this picture on the right here kind of indicates there is a lot of roughness to the surface, for the rest of the talk, we'll mostly be looking at maps kind of like this one, where we ignore a lot of the high resolution detail. So in this map here on the right, the dark gray areas represent land. This represents Greenland, for example. And we also have some light gray areas in the oceans that represent regions where sea ice is not really observed in any of our data. So we'll kind of leave those out of the analysis. The white areas are places where sea ice has appeared. So like I said, our goal will be to have a probabilistic model of sea ice thickness that somehow captures correlations in both space and time and is able to generate somewhat realistic sample sea ice thickness fields. So to give a broad overview of our strategy, we propose a two-stage model for sea ice thickness. In the first stage, we extend Hannah's sea ice extent model, which we call a contour model for sea ice extent, which allows us to sample boundaries for the sea ice. So here in blue in this plot is the representation of the true sea ice extent for October 2015. And then we're able to try to make some predictions about what we think the shape of the sea ice polygon is going to look like using this contour model. And so basically this allows us to generate sample ice-covered regions, and for a given ice-covered region, we model thickness conditionally. So if it's in the boundary that we generate, we say it's basically Gaussian distributed according to some Gaussian random field. And so basically we'll sample sea ice extents, and then for each sampled sea ice extent, we'll generate a model or a prediction for the thickness in all the ice-covered locations and kind of average over all those samples, both of the regions and of the thicknesses. So today I'll give a brief overview of both models. It'll be pretty high level, so please feel free to ask any questions. Okay, so first I'll start with the contour model. And so the goal of the model is to generate somewhat realistic ice-covered regions. And we think of these really as kind of like random polygons in some sense. So we need some model for random polygons. And so Hannah and Adrian and Cecilia, before I got involved, proposed a model that was called the contour model, where they would say basically, we'll define a sequence of randomly defined points, and basically by just connecting those points, you get some random polygon. In particular, the contour model first starts by assuming, a sequence of fixed reference points that kind of follow the land edge, or kind of the last place we imagine ice will melt. And we say that's kind of like the starting point for the ice. And then, so in this plot here, the red points represent that fixed edge. And then from each fixed point on this edge, we send out some sort of vector representing sort of the direction of growth of the ice. And these are all fixed. And then we define some sort of maximal length for these vectors, representing sort of how far we expect the ice might go if it was as large as possible. And then we basically just model, okay, what proportion of this line is actually covered by ice in a given month. And so this picture here represents, the ideas for this model for a subregion of the Arctic Ocean, which is the Greenland Sea. Okay. And so basically what happens is that once we have those random lengths, then we use the both endpoints of these lines in our random contour, and we basically just connect all these points to generate our random polygon. And the key idea here is that we'll be using some spatial temporal models to correlate the length of these ice-covered regions in both space and time to allow for spatial and temporal correlation in the resulting polygons. Okay. So this just formalize this a little bit more. Here I'm going to let vector C represent a contour, which we're going to define as a sequence of potentially random points, which we can connect to form a polygon, which will be our ice-covered region. Our fixed points will be, denoted BI, and they'll be located along the coast. And then we'll define some order set of line segments L, IT, representing the line at location I for time t, which extend from the fixed point with some random length y. Okay. For each of these lines, we'll define some sort of maximal length m, and then we'll basically just be modeling the ice-covered proportion of each line segment. So a number from 0 to 1, which will transform using a logit transformation, but we just basically truncate it at both 0 and 1 to make sure it's defined and to allow not for values that are too extreme. Okay. And so here again, we have an example line all these black lines represent example lines, and here the green line represents sort of what would the maximal length for a given line segment, and then the purple line represents, okay, what we actually observed for a different line segment, and we just kind of connect all of the observed lines there. And so in particular, we assume that the logit transformed ice-covered proportions, denoted W here, are multivariate Gaussian, where the mean is based on some sort of climatological average, meaning just the average for that month over a given training period, which I believe was about 5 years. And then some spatial temporal term that induces correlation between these lengths across space and time. So in essence, we use the AR1 term to say that the ice-covered proportions for segments that are kind of next to each other should be similar, and they should be similar to what they were maybe a month ago. So when I talk about time here, the time steps are really in terms of months. And for this contour model, at least, the locations are sort of the neighboring line segments. Okay. Okay, and so we carry out this modeling separately across 3 regions: the Greenland Sea here in green, which is what we saw earlier, the Kara-Barents Sea, and the Central Arctic. Now, in the Central Arctic, we don't really have a good way to define where the ice starts. So instead, we use a single central fixed point, which is the North Pole, or approximately the North Pole. And the line segments kind of spray out in a star formation from the center point, as seen in this image in the lower left. And so we train this model on several years of data, and then based on this model, we can obtain sample contours that represent kind of sample polygons that represent ice-covered regions. Okay. And so we do take a Bayesian approach. We assume some priors for all of these parameters, and then we draw from the approximated posterior for our ice-covered regions. So that really represents the first stage of our model. And in the second stage of our model, we propose a random field model for sea ice thickness within the ice-covered region. So on the right side of this slide here, we have 4 maps. The top left represents a mean forecast from our 2-stage thickness model. The bottom right represents the observed thickness from our satellite-based observations. The bottom left represents a climatological forecast, which is just the average thickness for the given month across all locations, across the 5 or so years on our training data. And then the top right represents the forecast from the dynamical physics-based model from ECNWF. And we see that because it's difficult to assimilate ice thickness observations, at this time, they weren't actually assimilating direct observations of ice thickness, so there is some bias in their predictions. So we propose to use a random field model for sea ice thickness. In particular, we're going to let F denote the thickness of the sea ice at any given location S and time t. And so basically we'll say conditional on S being inside C, being inside the contour, we'll say that F is drawn from a Gaussian random field. If S is not in C, we'll just say that F is 0. And so here you may be thinking, well, thickness can't be negative. Why are we using a Gaussian likelihood? And indeed, I think this was an issue that we wrestled with for a long time. But we ultimately decided that we're going to model F as being dependent on this parameter eta and this other parameter h. So those are the two I want to focus on. And eta just represents a kind of a climatological mean. And in truth, what we found was that the climatological forecast, if we just take the point-wise average across this particular month for this particular location, that actually captured most of what was going on with the thickness at a given location. And so the H term just represents those kinds of smooth deviations from that climatological mean. And what we found is that these were quite small, and so that even though the Gaussian model isn't restricted to be greater than 0, we found that this was actually it worked better than some other transformations we tried. So we'll model eta, or we'll let eta represent this climatological thickness at this given location for this particular month. And then H is a Gaussian random field with mean 0. That kind of represents, smoothly varying differences from this climatological thickness, smoothly varying in space and in time. And then delta just represents a small kind of measurement error. In particular, the spatial temporal correlation function we were going to use for the H component is AR1 in time, and it's approximately Matern in space. So in particular, for approximating this Matern field, we use the SPDE approach proposed by Lindgren et al. And so this basically uses a stochastic partial differential equation-based approximation to this Matern field on a fixed mesh of points scattered across our spatial domain. Both models are latent Gaussian models, so we carry out inference using the integrated nested Laplace approximation approach, or INLA, though nowadays I know that they're kind of moving away from Laplace approximations. And so this approach is really nice because it allows for fast approximate Bayesian inference, which gives us these kind of approximate posterior distributions, which we can sample from to generate predictions. Okay. And so to kind of just test our method out, we applied our method to generate forecasts for Arctic sea ice for months between January 15th and October 28th. And basically, we say for each initialization month, we generate forecasts for 1, 2, and 3 months out from that start point. And so for each of these months, We have basically, or for each of these initialization months, we have 3 validation months. And we compare our forecasts with the ECMWF physics-based model, a climatological forecast, and then in the paper, we also talk a little bit about a non-spatial version of our model. And so for making predictions, basically, we just have to sample ice-covered regions from our posterior, model thickness for all those ice-covered locations, and then draw posterior samples of thickness for this specified region. And then we basically just aggregate all these posterior samples of thickness. And our results basically find that, at this time, ECMWF wasn't assimilating direct observations of sea ice. So the errors in their model were, they had some bias. But we find that our model even does outperform the climatological forecast slightly in terms of RMSE. And we see that, as lead time increases, the error in our model goes up in terms of RMSE, but we're still outperforming the climatological forecast at 3 months lead time. We also found that in terms of coverage rate for marginal predictions of thickness at individual locations, we were able to get slightly conservative but pretty reasonable coverage. And the same was true for when we tried to get forecasts of sea ice volume by aggregating over location. Okay, so I'll quickly wrap up and just say that this paper tries to combine models of sea ice extent with a model of sea ice thickness to get short-term probabilistic forecast of sea ice thickness. And what we find is some reasonable performance. But our hope is that these kinds of probabilistic modeling methods can be combined with the physics-based models in the future as more of a post-processing method, because we believe the physics-based models will really only improve as time goes on. So I'll stop there, but again, I just want to say thank you to all of you for your time this morning, and then thank you to my collaborators, and thanks to the organizers for putting together this session.
Thank you very much, Peter. Very nice presentation. So we're just gonna pause for a few seconds to see if there's any questions in the audience. And either use the Q&A sessions or put in a question in the chat, or just speak up, if you will.
So if I may, just a quick question and comment, Peter. Did you have, you use the Matern covariance function in a stationary and isotropy way. It's the way you've shown us, right? I wonder if this contour has some kinds of anisotropy, particular directions where things are kind of different with respect to other directions. So did you have some kind of experience on that point?
No, so in some sense, for the contour model, at least, it's very, we only did stationary stuff. And for that one, it was really like just, AR1 correlation between the different endpoints of the contour. But I completely agree. Yeah, I think this was something that we started exploring, but we just didn't really have time to really get into. But I completely agree.
Yeah, thank you.
Any other questions?
Oh, hi, Peter. I have a very quick question. So your model has your model incorporated the physical process, or you will do that?
Well, we tried initially incorporating the ECMWF models as part of our model, but at the time, they weren't really assimilating sea ice thickness, so the bias that was introduced by that didn't seem to be actually helping at all. But we believe that as models improve, this would be kind of just a wrapper on top of any sort of physics-based forecast.
Oh, okay, thank you.
Makes sense. Thank you. Let's see. Jen, I'm just checking for any additional questions. Of course, if there are questions from the audience and you think of them later, you can add them to the Q&A feature here, and we can address them at the end of the session. Otherwise, please enter your questions now. But I think we could move on to our second presentation if everyone is comfortable with that. Jen?
Yeah, sure. So thank you, Peter, again for the nice presentation. So coming up next is Joshua North. So please feel free to take it away.
Hey, is this looks like it on my screen. Is that okay on you guys's?
Yes, looks good.
Yeah, well, first of all, thank you guys for organizing this and then getting us all together. It's really exciting and happy to be here. So my name's Josh, and I'm going to be talking about this paper in JABES, a Bayesian approach for data-driven dynamic equation discovery. And this is some work that I did with my advisors, Chris Weichel and Aaron Schlieb. Maybe. There we go. Okay, and kind of thinking about this problem, how it started. We started with this kind of role of dynamic equations and statistics, and a couple places they come up is in motivating some sort of component of a complex process, and where you could have some physical representation of that you want to account for. And so I have three examples here. The bottom left would be geopotential height, so that's some elevation in the atmosphere at which some pressure level occurs. And you can think of as this evolves in time, and you kind of see this like little wave cresting here. You can kind of model that with like fluid based dynamics is one option. Top middle, this would be coronavirus. This kind of falls under this compartmentalized type of model class, where you think about the population of infected to susceptible to removed or recovered kind of individuals changing. And this could be some temporal or space-time process. And then in the bottom right, this would be like sea surface temperature, again, kind of a fluid-based dynamics approach. And the whole idea is there might be some other random process going on with these, but if we can kind of account for that physical part of it and kind of address that, what else can we say? And simplifying the problem a little bit, making it a little bit more tangible, maybe. This is kind of an example based off of the Lorentz 63 equation, which you may or may not have heard of. This is kind of that form of that equation here on the right. And in essence, it's just a really simplified atmospheric process. So it's basically three processes, X, Y, and Z, and how do they kind of interact over time. And so the way this could work out is you might see this data on the left here, this kind of noisy data, and it looks kind of like this classical butterfly attractor. And you might say, well, I want to motivate some of this, the physics in this with the Lorentz equation. And so you might assign kind of this sort of dynamical process onto it. And there's various ways of kind of incorporating in there. And you may or may not want to specify or learn some of these parameters like sigma, rho, and or beta. And I would generally group this under this kind of class of mechanistic modeling, where you might specify some sort of mechanism that you want to account for, and it might be, and it generally is, physically motivated. This work that we have here is kind of going in that reverse direction, where we might want to take this kind of messy blob of data and say, well, can we learn anything about this? So can we learn kind of the underlying governing dynamics of this process? And so just to be clear, we want to basically go from observations of these three components like X, Y, and Z is over time to be able to write down this parametric form, which might be relating some sort of time derivative of the process to some function. And at the time that this was published, it was traditionally just done in the kind of computer science, applied math, and physics worlds. Although things may have changed in the last couple of years. But when we published this work, there were really kind of two main camps of looking at this problem. The first was with symbolic regression, and so that's where you might specify some mathematical expressions, so like addition, multiplication, and the reciprocals, subtraction, division. You could do like sinusoidal terms and logarithmics and so forth. And you basically search over some combination of those mathematical expressions along with your inputs to then kind of arrive at this dynamic equation. Super flexible, you have basically an infinite class of functions you can look at, but it's really computationally expensive. And so it doesn't scale very well. Its use was kind of limited. Again, this could be different now. But to kind of address that limitation, there was this paper, it acronymed to SINDY, which is Sparse Identification of Nonlinear Dynamics. And it basically took this kind of sparse regression approach. And so instead of searching over all sorts of combinations of these mathematical expressions and input space and everything, you basically define this library of potential functions. And there's ways of kind of defining these, and it kind of boils down to just doing some sort of variable selection procedure on that library of potential functions. Of course, there's the deep model analogs to both of these, and I assume that they've kind of really taken off in the past couple of years. But anyway, I'm going to focus on this work that I'm presenting today. Really kind of falls into this sparse regression camp, and I'll make that clear in just a moment. Okay, and so in thinking about this problem, there's a couple steps that kind of have to occur. The first is you have to translate from kind of this observed process X, Y, and Z to being able to relate derivatives of that process to some current state of it. And so to compute these derivatives, a lot of this prior work would basically take this numerical differentiation approach. And if I'm thinking about that sparse regression kind of problem, what that eventually equates to is you have to take derivatives, you have to compute this like dx dt, dy dt, dz dt, and then you have to compute a bunch of functions over on the right-hand side that you want to regress against. And the way they do that is they kind of take this observed data, do some sort of denoising, and then compute those derivatives and compute that kind of library to regress against. And it's really just this kind of numerical procedure, and everything's treated as deterministic after they denoise it. So they kind of just disregard any sort of uncertainty that might be encapsulated in that. And then the last kind of component that's kind of missed is this idea of uncertainty in these identified dynamics. And so you could think of, there's a bunch of plausible terms that could be in here, but how likely is it that X should be in this kind of first equation, or Y, right? Is there some sort of probability of that being included? And then of course, uncertainty on these identified coefficients, right? So like sigma, rho, and beta. Is there anything we can kind of say about that? And so a lot of this prior work didn't really address that. They kind of started from this denoised state, and then they had some sort of deterministic kind of search approach to identify all of these. And so we really wanted to kind of build upon that and address those key points. And so I'm going to just kind of do a really high level overview of how we kind of put this all together. And so this would be kind of how I framed the statistical model, kind of this hierarchical approach. And so I define this vector v, which would be some vector at time t of our observed data. And so kind of building on that, the Lorenz example, where I have three kind of components, so x, y, and z. This could be at most a length 3 vector, but of course you could have data that's missing in time. So it could be, length 0, 1, 2, or 3. And so then to kind of map from this, partially observed data vector to a fully observed latent process, which I would denote by U, we have this matrix H. And then I have this maybe unconventional notation where I want to denote derivatives of that process U with respect to t. So if I want, say, the jth order time derivative of that vector, that's how I'm going to denote this. And so then the way I might incorporate a dynamical equation into this framework is, by convention, I tend to take the highest order temporal derivative on the left-hand side. And I'd say that's equal to this function m, which is this potentially nonlinear evolution function. And this function takes arguments of the process u from kind of the 0th order, that would be kind of no derivatives, up to the j minus first derivative, right? And this could have all sorts of interactions and everything in there. And the first thing we want to do is start thinking about how do we compute all of these kind of latent processes, these U0s through UJs. And so what we end up doing is just adopting this basic expansion. And so now I would write that process, so say UT of this lowercase j, that's going to be approximately equal to this product of A and phi, where A is going to be some just matrix of basis coefficients, and phi are going to be fixed known and differentiable basis functions. And we have this restriction that they have to be differentiable up to at least the jth order. And then what we can basically do is just kind of substitute that in. And so now you can see that this form above is written in terms of this basic expansion. And I want to say, in the prompt for this, we were said we could say something about things learned. When thinking about now a space-time process, which we did, these basis functions take on a little bit more of a complex form, but just something to kind of think about there. Okay, then the next step is we basically want to reparameterize this to be linear in the parameter space. And so it's still nonlinear in terms of this process space, this U, but we are going to assume linearity in the parameters. And so this basically boils down to making this relationship here, where M is going to be some sparse matrix of regression coefficients, and F is what we're calling this vector-valued nonlinear transformation function. And so this is where we would adopt that kind of library-based approach that's in the sparse regression procedures. And we have to define some functions in F that we want to search over. And this is kind of the most subjective component of this kind of whole area where you kind of have to put some thought into what you want this function F to be. And so it turns out for most ODEs, it can generally be polynomials and interactions of these polynomials, although you could definitely add other terms. But thinking forward, that's not the case for PDEs. Those tend to be much more complex, and a lot more thought has to go in there. But anyway, this is kind of the general idea here. And now when we think about kind of estimating things, there's a lot of kind of hyperparameters and stuff in here that matter. But I'm really going to only focus on two components, which is estimating A. And so correctly estimating or characterizing A will get us kind of that process U and all sorts of derivatives of it. And then also estimating M, which is how we kind of determine that final dynamic form. And so in terms of estimating A, it can be slightly tricky because F here is problem specific, right? If I have kind of two different dynamic problems that I'm considering, you might want to tailor F to that problem. And A is embedded in F, and here I only show it, once. But in reality, it's however many functions you have in F as a minimum. And so this A is really just kind of floating around all over the place. And so what we do is we rely on the stochastic gradient descent with a constant learning rate. And it's this kind of posterior approximation technique. Although I will say you could use any sort of gradient-based MCMC method. And the whole idea there is that as long as you can compute derivatives of this function F with respect to A, you can use any of these kind of gradient-based methods and kind of rely on automatic differentiation, and it makes things really modular and a lot easier to work with. Okay, and in terms of estimating M, this ends up being pretty tricky, especially as problems increase in complexity. And so for the work that I'm going to show here, sorry, let me back up real quick. So to estimate M, we really want this notion of inclusion probability or importance, right? So we want to know, which terms of M should be there, and thereby identifying which components of F should be in this dynamic equation. And so it really just boils down to this variable selection procedure. And so you could kind of use, whatever you want. For this problem, or for the ODE problem that I'm showing here, we use SSVS. And then in the spirit of lessons learned, as things get more complex, SSVS kind of breaks down. And so the reason is it doesn't enforce sparsity. And when you think about these much more complex problems, you really need to enforce sparsity. And so the whole point is that if you have some kind of nonlinear term in there in your model, and you have a really small coefficient value in front of it, that can still be hugely important. And so if you can actually just kind of remove that importance, so set it equals 0, remove from the model, things behave a lot better. And so for kind of future work, we move towards the spike and slab. The other thing that kind of starts to show up as you get into more complex problems is this issue of multicollinearity. And so what I have on the right here, this figure, if I take some hypothetical library of all of these terms here, and the x here would denote a derivative in some spatial dimension, and I compute this vector f, and I evaluate it all kind of space-time locations, and I compute the correlation of that kind of matrix. And that's what I've shown here. And so you can see there's a lot of values near 1 or near -1, and so this issue only kind of shows up even more with complex problems for a variety of reasons. And so what we end up doing is we kind of have this adjusted spike and slab procedure based off of this condition number of f And that allows us to kind of handle these much more complex kind of PDE-based problems. And then we also talk about how the kind of prior work on this, where they have these kind of deterministic search procedures, this kind of equates to like a probabilistic approach to some of those procedures. Okay, so that's kind of the overview there. I just want to talk about a couple examples now of what we did. And so these first two examples I'm going to show are basically cases where the kind of previous work really couldn't handle. And so this first one, this is taken from the Lorenz 63 case. So again, that kind of weird butterfly looking attractor there. If I were to expand it on each one of those components over time, it looks something like this on the right. These red dots, these would denote, say, some noisy observed data. That underlying blue line, that's the truth, but I included it because hopefully you can see it, there's kind of gaps in there, and that's just to note areas where there would be missing data. And so data like this wasn't these kind of prior approaches couldn't handle this for a couple of reasons. One is, turns out this is actually too much noise for these other approaches to be able to estimate anything. And the second one is they can't handle missing data. So we need to see, like, if we can accommodate something like this. And so what we do is we specify some large library of potential functions, and then we kind of fit our model. And so here's that target, that true equation that we want to target. And then now this next line, this is the posterior mean of our identified equations. And so again, we have this kind of variable selection procedure. We have a probability of each term being included, and we have some threshold, which is saying, like, any term with higher probability than that threshold is considered identified. Anything lower is not considered identified. And so here's our identified equation, based on that threshold. I show y in red here because we actually don't identify that. So I just want to point out that we do miss one of these terms. But we do identify the 6 of the 7 terms correctly. And of those 6, the bolded ones are where the 95% credible interval covers the truth. So we correctly identify, 5 coefficients, but we correctly identify 6 of the 7 terms. And we can also get, there's an underlying probability of each of these terms being included, and there's some notion of the uncertainty on those parameter estimates. So this was fun. We could kind of identify it for the Lorenz case. So it was nice to see. The next example I want to highlight, which is one that a lot of these other procedures, well, I don't think we saw this considered at all, but they definitely cannot handle, is this question of a missing system. And so by that I mean, let's pretend I only observe, say, y and z. Can I, if I think that there might be some third latent system, can I learn that system? And as a real quick side note, in terms of kind of what is or is not kind of identifiable given the missing system, there is some limitations. So it's based off of Taken or Tauken's theorem. I don't know how to say the name, but basically, if you can reconstruct one of the 3 systems from lags of the other systems, it's identifiable. And so in this case, z is not an identifiable system given x and y, but either x or y are identifiable given z. So there are some limitations here. But considering those limitations, we're going to pretend that x is just missing. We don't observe it at all. We only observe, say, y and z. And the question is, with a 2-dimensional input, hypothetically 3-dimensional latent space, can we learn that missing system? So again, we specify some library. We feed in our model. And after we kind of consider that threshold for inclusion probabilities, this is our identified equation. Again, that one term is in red because we just don't identify it, but we do correctly identify 6 of the 7 terms, and of those 6, in this case, only 2 are considered cover the true values. But I do want to take a quick sec and say, if you look at the top here, there's a black line underlying all of this. That's the kind of true system. The blue lines are posterior mean, and the red shaded region is our 95% credible intervals. And so this one on the left here, x, was completely unobserved, right? And so you can see is that the posterior mean almost perfectly overlays that black line, and we get some pretty reasonable credible intervals. And there's some reason why they kind of look like this, but I'm not going to jump into it. And so the whole point is that from only observing y and z, we can not only learn what this system might look like. We pick out the correct terms that should be in there, but we can see that it's also pretty close to the truth. So it's like a pretty cool example where kind of you get something out of nothing in a way. Okay, this last one I want to show is on sea surface temperature, and this is going to be a little bit black boxy. I'm not going to show the resulting equation here because it was kind of too much to show on a slide. But the whole point of this was, can we learn the dynamics of the ENSO cycle through the temporal EOF? So here I'm going to show kind of that we are able to learn the dynamics by way of predictability. And so in case you're unaware, the ENSO cycle is this kind of cyclical pattern in ocean temperatures over the South Pacific. So here's like Australia, here's South America and Central America. And so it's kind of this warming and cooling pattern that happens kind of out here. And so what we've done is we take data from 1926 up to either March of 97 or February of 2015. We're going to consider two different events here. And we compute the 10 leading temporal EOFs. So that would be like the 10, if you took the singular value decomposition of kind of this process, that would be the 10 temporal basis functions. With those 10 EOFs, we then feed in the model. We try to learn these dynamics. Given our identified dynamics, we then project forward in time 12 months. So from like April 97 to March 98, and then March 2015 to February 2016. Map back onto sea surface temperature, and then estimate or compute what's called the Niño 3.4 index. And so that's basically the average sea surface temperature over this kind of box somewhere out here. In panels B and C, the blue line would be the Niño 3.4 index taken from NOAA, and then that red line would be our posterior mean, and the shaded region would be our 95% credible intervals for that Niño 3.4 index, which has been learned from our kind of dynamic process. And so what you can see is actually, I should say real quick that kind of leading up to this, there was really no inclination that there would be some pretty big swing in the ENSO cycle. And so what we're able to do is by way of these kind of EOFs and kind of the dynamics that we learned from them is actually project forward, reasonably well, kind of 12 months into the future. And so this kind of falls in this like sub-seasonal to seasonal predictability, which is, I think, kind of gaining traction right now. And so it's kind of cool to see that we kind of jumped into this on accident, but it just shows kind of the ability of our model to kind of learn these dynamics by way of kind of predictability. I have two other examples that I'm not going to show because I'm kind of up on time here. But just to recap, this is kind of the statistical treatment to this dynamic discovery problem that really lived in the kind of computer science and physics kind of realm. And here, this was kind of our first foray into our ability to learn these kind of complex nonlinear dynamic equations based just off of the data. I showed a couple examples of its robustness to measurement noise and missing data, and even this kind of cool example with the missing component. And then our ability to provide uncertainty quantification and exclusion probabilities to these kind of learned terms. Here, I really only showed two examples, two Lorentz examples of sea surface temperature, but we have a bunch of examples going all the way up through kind of PDs and so forth. So if you're interested, please check it out. I think that's all. Thank you.
Thank you, Josh. It's a very nice presentation as well. So any questions in the audience?
Yeah, I have one quick comment, Joshua. Well, congratulations for this presentation. And the thing is that you said very well that usually solving ordinary differential equation or stochastic differential equation, they go more, not the stochastic, partial differential equation, right? They go more on the deterministic way rather than on the stochastic way, right? What you've done here basically is putting some stochasticity to go into uncertainty estimation, right? Of
Yeah.
that is a step forward in these dynamics problems. This is one thing. Another thing is, I don't know if you've heard about these integral differential equations. They're more on the let's say LGCP, which is a log Gaussian-Cox process where the intensity depends on the exponential of a Gaussian process, right? But then the problem there stands in the Gaussian process at time t+1 depends on the integral of a transformation of what is happening on the Gaussian process at time t. Yeah. That transformation is really hard to estimate. Basically, it's based on dynamics. And then I mean, the paper I've seen there is, well, let's assume that this transformation is known, and if it is not known, well, we don't know, then we just assume it is the identity, and then we just integrate the previous one, right? Now what you do is, yeah, a way to solve that problem. I mean, we have f of something, of a Gaussian process there in the space or the space and time, and basically you try to learn the dynamics behind that. So basically you are estimating f of the Gaussian process. So for me, it's you are providing, I mean, although you haven't mentioned that directly, you are kind of offering a solution to that problem. So it's perfect in the way I see this thing.
Well, thanks, Sorry. That's really kind of you to say. Yeah. I mean, I think there's a lot of cool stuff that's kind of in this world. And I actually think that a lot of the, computer science and applied math problems, just adding like some uncertainty quantification to the stuff that they're doing is like a really hard problem, but they're doing it in such like a really cool, novel ways, and kind of how you're talking about, like, we have to make these assumptions, and they're kind of dealing with a different thing. How can you kind of cross those boundaries? I think there's a lot of cool work in that area to come. So yeah. Thank you.
Any other questions, comments?
If we still have time, I would also like to ask a question. So, Josh, you in the middle, I thought you are going to approximate those dynamic differential equations using some function, complex function m. And so I thought you will skip over those differential equation, but at the end, you did estimate the parameters in the differential equations. So what are those m functions like? Are they not approximating the differential equations, or they are? Yeah.
So we
missed something.
Yeah, so we obviously had to make some assumptions about what equations we could learn. Basically, it has to be linear in the parameter space. That was the big assumption. But as long as it's some dynamical equation that kind of falls within that, I'm not going to say that it's everyone, but we were able to estimate a lot of or recover a lot of those. So I have some examples of like within the partial differential equation space, so like space-time ones where we can still do that. But again, linearity in the parameters was really that big kind of caveat. So hopefully that answers your question there.
I think I need to read your paper.
Yeah, let me know if you have questions. So
thank you.
Thanks, Bo.
And that's a good reminder. We can include the direct links to all of the papers in the chat. We did include those in the introduction and the announcement about this session, but we'll do that as well to make it easy to access. Thank you, Joshua. Appreciate it. And we will move on now with Jen's permission to our third presentation.
Great. So please take it away.
Oh, thank you. Let me first enter full screen. Okay. Oh, okay. Can you see my screen? Okay.
Yep.
Okay.
Yes.
So it's my great honor to speak in this session, and a great surprise when we received that wonderful news. So I'm going to talk about trend point estimation for spatially correlated functional time series. When I worked on this, I was at UIUC, and I just moved to Washington University in St. Louis. Wanted to thank my two co-authors. First one, Meng Chen, was my former student, and she's now at Meta. Trevor Harris was another my former student, and when we worked on that, he was at Texas A&M University, but recently just moved to University of Connecticut. So you can see all of three had trend point already in the last 3 years. And also, it turns out that they both are busier than me, so do not have time to present this. So, but it's great that they are busy. So I'll first start with the trend point in time series, because it's such a classical topic in time series. And the methodology for change point detection estimation for time series mainly falls into these two categories. One is at most one change. So the time series only has either no change or one change or multiple change points. So this shows an example of a time series and with its mean. So this one, we do have 1, 2, 3 change points in the mean function. But if we only look at this part, it will only have one change point, so can be solved by at most one change. For change point detection estimation, most methods are based on this Q-sum statistic. So it's literally just take a cumulative summation over the time series and then subtracted by some sort of expectation of the summation. So I will show more details for Q-sum later. And then since my talk will be about functional time series. So now I introduce functional data using this example. So this 35 curves are the smoothed version of monthly mean temperature from 35 weather stations in Canada. So each curve represents monthly mean temperature. Is a smoothed version, and each curve is considered functional data. So suppose that we observe those 35 curves at different time, and then this will give us functional time series. So no matter it's a univariate time series or functional time series, as long as it's time series, it's possible to have change point. So there is change point issue for functional time series. And in the recent years, there are already a lot of work to detect the change point for functional time series. And primarily, they focus on the at most one change and also mean change, because for functional data is already complicated. And then most methods are based on dimension reduction. So they first project the infinite dimension of functional data onto a finite number of principal components, and then the change point methods will be developed based on those finite number of principal components. But when you do any dimension reduction, you would have the risk of losing information. So Alexandra Au, in this paper, they proposed fully functional methods to find a change point in mean. So I particularly list this paper because lots of comparison of our method will be to compare to that, because that was a cutting edge paper when we started to work on that. And then now the last piece of information is a spatially functional time series. This one is the reason that we look at spatially indexed functional time series is because this type of data structure is very common for environmental data. So for example, the 35 weather stations, I mentioned that data set in Canada. So at each of those weather stations, you could observe a functional time series. And also because the weather stations are in a spatial domain. So that gives us a spatially indexed functional time series. And then when we try to study the change point problem for that, we found actually very few papers studying that problem. And basically there is one group, Gramenko's group. He was a PhD student at that time. His thesis was studying on the spatially functional time series. And in particular, this paper is most relevant to ours. They detect a change point for a spatial functional data, and they considered the spatial correlation in their method. But one restriction for that method is they assume a common break time. So every functional time series in this spatial domain assume a common change point. So that method is very solid and very interesting, but we think if we observe those spatially functional data in a large spatial region or large geographic region, and then this assumption would be unrealistic. So I'll show you an example. So in this example, we have, we have 16 weather stations in California. And for each one, we have 50 years of daily minimal temperature. So the daily minimal temperature is a functional data, and we have 50 years of 50 curves of such functional data. And then we applied the fully functional methods on each of the weather station to detect a trend point and estimate the trend point. So those are the results. The color represents the trend point. And we learned two things. One is, it seems like the trend point varies a lot over the California. So that indicates that it's a not a good idea to assume common trend point for all those weather stations. And another thing we learned is it seems like it's spatially clustered. If they are close, if they're neighbors, and they seem to be similar, the trend point. So this motivated us to propose a more flexible trend point estimation methods for this spatial functional data. And in our method, we will allow both the break time and the amount of change to vary spatially. And we will, our work also focus on the mean change and at most one trend point following the previous papers. We will take spatial correlation into account in our method. And there are two reasons why we consider spatial correlation. One is to respect the spatial continuity. So we do see that the neighbors tend to have the similar trend point. And so we use spatial correlation to take care of that. And on the other hand, if we use spatial correlation appropriately, we can improve the estimation of trend point. So this is the reason why we wanted to take spatial correlation into account. And our method is also based on Q-sum statistic. And the main idea is based on some Q-sum related statistic, we kind of approximate the mean of that using a piecewise linear model. And then we fit the piecewise linear model on all locations using a Bayesian hierarchical model. So that way it's very easy to take account of, to take into account spatial correlation. So now let's introduce the methods in more detail. So we use the XST to denote the functional observation at location S, time t, and U is just index for the functional data. And we assume X is a real valued square integrable function, which is very common for functional data assumption. And then we assume that our functional time series follow this model. So this has mu s, so this is the mean function at location s. And then this part is the change is related to the trend point. So the first look at this indicator function. So the ks star, this one would be the trend point at location s. So if there is a trend point after t, the mean function will become a mu s plus delta s. So this delta s is also called the trend function. And then the epsilon are the errors for this functional data. And we do have some assumptions for the errors. So we allow them to be temporally correlated, and also they are identically distributed, although they are not independently distributed. So basically we assume that the epsilon follows a mean zero second order stationary and isotropic random field. So these assumptions allows us to consider all the changes in the observations are due to the mean change, not due to the errors. And then suppose we observe functional observation at n spatial locations and t time points. So the trend point in this functional data can be described into this hypothesis. So basically it's a delta s, the trend function equals 0 or not. And this trend function is a curve also. Trend function equals 0 means that everywhere in this trend function should be 0. So if this is 0, there will be no trend point. If this is not 0, then there is trend point. We will use a Q-sum stat. So here we wanted to introduce Q-sum stat. So in this Q-sum stat, there are 2 components. So the first one, you can see it's really just cumulative sum from t equal 1 to time equal k. And then this part is just like if you first take average of all those x over t for all time points, and then multiply this k. This is the time, the time step you are taking summation. So basically, it's a cumulative summation subtracted by kind of like expected value. And for this Q-sum stat, by definition, at the 2 ends, when k equals 0 and k equal t, the 2 end would be 0. So our paper, they also based on this Q-sum, and their test statistic is to first find the L2 norm of this L2 norm of this Q-sum stat, and then the maximum value of this Q-sum square L2 norm is their test statistic. If this is large, and then there is trend point. If this is small, then there is no trend point. And the trend point is estimated at the time point when this one takes its maximum value. So because Q-sum stat is used very in most of the trend point literatures, it's mainly because the Q-sum stat really contains information of a trend point. So our method will also use Q-sum as the building block. So to simplify notation in introducing our method, we first use a y to denote the L2 norm of this Q-sum. And as I mentioned, y also equals 0 when k equals 0 and k equal t at those 2 ends. So now you can see actually, no matter what, actually, I think we also did some type of data reduction. So now this YTKS is a spatial temporal random process, because this is after taking L2 norm, this is just a scalar value. So previously we have spatially indexed functional time series, and then now we reduce that into a spatial temporal random process. And our method is based on the properties of this process. So now let's study the properties of this process. So under the null hypothesis, when there is no trend point at location S, and then we can derive this asymptotic distribution of y. So the asymptotic distribution can be described by Brownian-Ridge, standard Brownian bridges, and we can easily calculate its mean and variance. However, under the alternative hypothesis, when there is trend point, we were not able to derive the asymptotic distribution of y directly. But we were able to find a z process that seems like should be very close to the y process, in the sense that if you take square root and then take the difference, and the difference would go to 0 in probability. And for this z process, we can calculate its expectation and variance with analytic form. So we think if we can approximate the mean and variance of the y process using this z process, and then we can develop the method using those properties. And then we did some numerical experiment to kind of evaluate how close the asymptotic kind of theoretical approximations to empirical results. So we did an experiment with 4 different combinations of the number of time points and also signal to noise ratio. So among all those, and this is we look at the empirical mean and the theoretical mean. So the blue is from the empirical, and the red is the theoretical approximation. So we look at both the mean and the variance. And across all the scenarios, we found actually the theoretical approximation and the empirical results match really well, especially the mean. And the variance seems like have some little difference, but it's very minor. And we also find that actually theoretically we can verify that the mean always attain the maximum value at the change point. And the shape of this mean depends on the amount of change, or you can say the signal strength. When the signal is stronger, the mean tends to look more pointy. So based on, and then also the variance is definitely not constant. The variance seems like also become larger at around the change point. So based on this, I also wanted to talk more about this. So based on this shape, and we think, so the change point is just like when when this mean function becomes the maximum value. And so if we can use a piecewise linear model with two pieces to approximate the mean, and then as long as we can find the peak at the right time, and then we can identify the change point. So based on that, and then we look at also simulation examples. So in this plot, I simulate two Y process, the blue and the red. And then I fit two piecewise linear model with two pieces. And so I wanted to use the intersection of those two pieces to approximate, to identify the change point. So for this red one, so there are two Y processes. For this red one, we're very lucky. We get almost exactly the change point when we look at the intersection of those two pieces. But for the blue one, due to the randomness, we do not, so this one will not match with the change point. But it is fine because all the estimation has uncertainty. So as long as we can quantify this uncertainty of estimation, and then probably we will be fine. And to accurately quantify the uncertainty estimation for this model fitting, and thus the intersection of those two pieces, we should try to more accurately model our errors. So remember, the errors is not constant at all. So we need to try to use our theoretical approximation to model the varying, the non-constant errors. And another point we wanted to make is the shape of this Y process depends on the break time, where the break time, if the break time is here, and then it will be like this, and how pointy it is depends on the amount of change. So translate to this piecewise linear model, it basically means that the slope and also the intersection of those two pieces will be determined by the break time and the amount of change. So if those two quantities are spatially correlated, let's say they are some more similar when the locations are close, and then that will translate into our model assumption that the slope and the intersection of those two pieces would be similar at neighboring locations. So this comes to our method. And so we first define a piecewise linear model, and because we have the zero on both ends for this Y process, we can use one slope parameter for this piecewise linear model. And then we model the slope parameters and the joins of the two pieces as spatially correlated process. And then we jointly estimate all the piecewise linear model across all locations together and to estimate change point. And we put them in a hierarchical model. So in the likelihood process, we just model this Y process as a piecewise linear model. And for the errors, as I mentioned, that the errors have non-constant variance. So we try to model the variance of the errors using the theoretical approximation of of the error process. And then we use a separable space-time covariance function to model the error, the correlation structure in the error. So, and then I will skip some slides due to time constraints. And then in the prior stage, we model all the parameters like slope parameter, and this is a change point, the change point parameter, and this is some nuisance parameters. We will model all those parameters using the spatial correlated Gaussian process. Of course, they have to go through some transformation, and you can choose any spatial covariance matrix, spatial covariance function, and for simplicity, in our paper we use exponential. And then we did some numerical experiments to evaluate our method and to compare with the previous methods. So I skipped all the data generation approach, so data generation stage. So let's just look at the result. So this is a root mean square error of change point estimation. And we compared the methods. Our methods is a Bayesian hierarchical model and the fully functional. And this is a Gramenko's method. And those are phi equal 2 and 5 represent weaker spatial correlation, stronger correlation. And the rho equal 1, 2, 1, or 1.5 represents a weaker signal. And this is a stronger signal. So, and for this one, we can see that the Gramenko, because they assume constant change point, but our simulated data has spatially varying change point. So there is no surprise that their methods did much worse than those two. So in this panel, we just removed the Gramenkos and zoomed in those two methods so we can look more carefully what's the difference between our method and the fully functional method, which just estimate the change point at each location independently. And then we find that across all scenarios, our estimation have lower root mean square error. And the advantage is more similar, the advantage is more obvious when the signal in those two, when the signal is weaker, and also when the spatial correlation is stronger. And so those give some examples of one simulation run. And in this simulation run, we do have stronger signal. So both methods, like the red is our method, and the blue is fully functional methods, and the black is the true. So, but yeah, with a strong signal, both methods are doing pretty well. But we can still see that our method has like a better. So, well, especially when the change point is close to the end, we have smaller confidence interval. I feel like I changed some. Yeah. Okay. I think that somehow my slides, I skipped some slides, and basically this slides is in the simulation, using simulation to study to examine the coverage and also the length of the credible interval between the two methods. And again, we find that the coverage of our method is much better, close to the nominal level, and but it's not at the cost to have a wider credible interval. Actually, the credible interval is much shorter than the fully functional methods. And so in this plot, the bars represent the credible interval, or for the fully functional methods is confidence interval. So we can see that our credible interval can be much shorter than the confidence interval. So our intervals, uncertainty interval, is much more informative. And this is another example. In this example, we have weaker change point signal. So now the fully functional starts to struggle a little bit, especially when the change point is at the edge. So this when the change point is, so our time domain is from 0 to 1. So this 0.2 and 0.8 means if the change point is close to that means it's close to two ends. So when the change points are close to the ends of the time series, and the fully functional methods often miss it, but we can still capture it because we consider the spatial correlation that strengthened our estimation. So now come back to the example that I used to motivate our study. So in California, we have the 16 weather stations, and this is a trend point estimates from the fully functional methods, and this is from our method. So you can see the color. This is our estimates are more colorful than this, and it's because the trend point estimates from our method has a larger span in time. And so if we look at the trend point estimation in this way, so you can see that we can see that the red is our method. We can estimate the trend point when it's close to the end of the two ends of the time series. But the fully functional methods tend to always estimate trend point around the center of the time series. So although we cannot verify what is true, what is not true for real data, but this observation is consistent with what we have found in the simulation. And we did another fun, kind of like a fun example. So that time it was made of COVID. So, and we often heard that the age distribution has shifted from the senior people at the beginning to the junior people. And then we look at the Illinois county level COVID-19 cases. And so we look at 95 days during which it seems like the age distribution might have shifted. And we look at non-age groups, but the unknown has very few cases, so we removed that. And then we first smooth the data using Fourier basis function to make the age distribution become a functional data. And then we estimated, the trend point using both fully functional methods and our methods. So the color represents the trend point estimation. So again, you can see our estimates are more colorful because we cover a larger time periods, our estimates. And this gives a more clear picture of our master estimates versus theirs. So again, we see that our credible interval is much shorter than theirs, and we can capture some of the trend point close to the ends of the time series. And for this one, we're more kind of like interested in what's going on. So we pick two counties, Champaign County, where UIUC is, and then another big city, Peoria. And so the blue is the after trend point, and the pink is before trend point, and the dark blue and the dark red is the mean of those functions before and after trend point. So we do see that after trend point, and this seems to like to have more young people involved, and similar here, but this one seems more obvious. And for Champaign County, we estimated the trend point estimates is January 16th, 2021. And we look at the university calendar, and we found that university residency halls were open for the spring semester on January 6th and 17th. So we think, because UIUC population is really very non-ignorable for Champaign County population. So we think this coincidence will not be just accident. That likely explains why the age distribution has shifted so obviously in Champaign County. So quickly give a summary. So we develop a Bayesian hierarchical model based on the QSUM process for trend point estimation. I don't know whether I made it clear. So we only look at the trend point estimation, but not the detection. For the detection, we rely on some existing methods. And we allows the heterogeneous break time and the trend point, but using spatial correlation, we can preserve spatial continuity. And our method is our method is based on approximating the Q-sum process using piecewise linear model. So it's very easy to synthesize all the information across all locations to estimate the change point. And we found that our method shows a big advantage of change point estimation, especially when the change point are close to the edges of the time series, compared to the methods that just estimate the change point at each location independently. And that time we consider combining detection estimation in the future. And we just actually did this work, but I was just not ready to show it now. So that's all my presentation. Thank you. I hope I didn't. Yeah, thank you very much.
Okay, thank you, Bo. It's a very nice presentation. So now the floor is open for any questions, comments.
Yeah, I have one comment, Bo. It's really fascinating seeing that the way you go from the functional stuff into just a space-time process, it's by considering the L2 norm over the Q-sum, right? Which is, I mean, and you get really good results. So I'm just wondering how, in a sense, you are losing information, right? Going from a continuous functional form, then you just reduce that. It's like you project that into just a space-time data, and you follow your procedure with your Bayesian analysis with the space-time data. So in a sense, you are losing information, but in practice, no, you are gaining information, and you do a very good job. So I wonder if you just, I mean, you've been thinking about that thing. Even you lose information in your procedure, but you really gain lots of things there. How do you, balance these two things?
Yeah, thank you. Thank you for the question and the kind of comments. So we think the reason that we do better than, let's say, the fully functional method is because, yes, we did lose the information. This is 100% correct. But all the methods for like functional data, functional time series change point, they also kind of has to reduce the functional data into some like very low dimensional data. So they also lose the information. So in terms of that, we probably lose a similar amount of information. But because we consider spatial correlation, so when the neighbor, if the neighbor, let's say, if for one particular location, I don't have a very strong signal to estimate its change point, but my neighbor actually has a stronger signal. And then the correlation will allow this particular location to borrow the strength from its neighbor. Or even both have a weak signal. And you could consider they can act as some sort of replicates. So when you start to have replicates, and then you can also estimate better. So this is a kind of intuitively, I think, why it can do better than the fully functional method.
I see. Yeah, thank you.
Yeah, thank you.
Any other questions from the audience? So as a reminder, you can always ask questions later on directly to the speakers if you will. So the video is going to be posted on IBS website in just a couple of weeks.
Yep, that's correct. And we do have one other agenda item today before we break, and that is to announce the winners of the 2024 Best JABES Paper Competition. And as you can see on your screen, I believe, we'd like to recognize the 2024 winners. Daniela Cisneros, Arnab Hazra, and Rafael Husser, the winners of the JABES 2024 Best Paper Award. Their paper, Spatial Wildfire Risk Modeling Using a Tree-Based Multivariate Generalized Pareto Mixture Model, hope I said that correctly, was published in the recent February 2024 issue. So we look forward to hearing their paper at the IBC in Seoul in July of 2026. The specific week for IBC is from the 12th to the 18th. Exact dates during that period are to be determined. We're working that out with our venue, but please mark your calendars for that. I will just mention a quick thank you once again to Jen Lee, Jorge Mato, and all of our presenters today. This was a fantastic session. And on behalf of IBS, I want to thank you all, including our attendees, for joining us for this very special award session. And as a reminder, a recording will be available next week. That is the end of our program. We are over a few minutes. We appreciate you staying on. But if you need to, you may now exit the session. And thanks again, and we'll see you at a future Journal Club. Take
Thank
care.
you, everyone. Great talks.
Thank you.
Congratulations again.
Thank you.
Absolutely.
Yeah.
Well done, everybody.
Thank
Okay.
you very
And nice
much.
to meet you all. Take care.
Bye.
Okay,
Bye.
bye-bye.